Yeah, so we're still in section 7, talking about inverses. And where we left off last time talking about inverses is we were talking about writing the inverse of a function when the function was represented as an equation. We're going to continue doing some more examples of that. These provides us a nice opportunity to review some other algebra skills that we hopefully still remember, but might need a little bit of a refresher on some of the finer points of. So let's say our function is p of x equals 3x squared minus 4. Remind me again what the procedure is for finding the inverse when our function is represented as an equation like this? Okay. And solve for, well, not if you're swapping the x and y's first. So, Trevor, you weren't necessarily wrong, but their second step was not correct if yours was the first step. So, usually the way I like to do this is I'm going to start by rewriting this from function notation into y equals notation. And then I'm going to solve for x, and then swap the x's and y's. Now, you could swap the x's and y's first and then solve for y. That's okay, too, for the most part. But I like to do it solving for x and then swapping the x's and y's. And I'll explain to you guys, or give an example of why that's often, well, sometimes makes things a little clearer what's going on. So if I want to solve for x, what's the first thing I should do in this particular instance? Add 4 to both sides. Good. Then what? Divide by 3. Good. Then what? Square root both sides. Is that right so far? Is that right so far? Is that right so far? So by this point, you're probably thinking, oh no, there's something wrong here. What did you say, Maya? That's fine. We're not going to worry about that, although, there you go. What was that? Plus or minus, yeah. When we square root both sides of an equation, we need to have a plus or minus. And I admit there is a square root in the denominator, and you could fix that, but that wasn't the bigger issue, because that's a question of style, not right and wrong. So it's still the same, has the same value. It's the same function. You just kind of like reduced it a little bit. Without the plus or minus, though, this was not correct. I will be clear about when I care about that. And unless I say specifically, like, these are the kinds of situations where we care about this, you don't really need to care about it. More often than not, if there's an x or a variable in the expression, I wouldn't worry about it. So like in this one where you have the y plus 4 in the numerator, I wouldn't worry about rationalizing a denominator in those kind of situations. If it was like square root of 4 over 3, then I would worry about it, where it's just numbers. Allison? Of course. Okay, and then the last step would be to swap our x's and y's. So we can say that p inverse of x is plus or minus the square root of x plus 4 over 3. Did you guys notice anything about p inverse of x? you notice anything about P inverse of x? No. That's fair. The answer is no. The answer is no. Is P inverse of x a function? No. Why not? What part of this is the problem? It's that plus or minus, right? So for any value of x, let's say any non-zero value, anytime you're getting a non-zero number out of that square root, you're getting two y values for that given x value. Now, that's kind of a problem, right? If we wanted to make sure that our inverse is a function, we can fix this by doing something called restricting the domain. And we mentioned this a little bit in Algebra 3-4 last year. So what we do is on the original problem, we'd have some caveat like x has to be greater than or equal to 0. We're not going to worry about how we decided that as the restriction for the domain. We'll just kind of take my word for it that that's the appropriate restriction. Trevor? Do not. Of course. Now that doesn't change any of our steps until we get to here. If x has to be greater than or equal to 0, then x can't equal plus or minus the square root of something, right? Because what kind of number comes out of a square root? A non-negative, right? You always have to be positive or 0. You can't take the square root and get a negative number, correct? So when I have this plus or minus out front, I can't have the minus part to it because that would give me a negative result. And x has to be non-negative. So that allows me to get rid of this. And now that P inverse of x would be a function. Now, do I expect on a problem like this for you to do that? No, I do not. I'm showing you this because this is something we will need to worry about a little bit later on when we construct the inverses for the trigonometric functions. But we'll cross that bridge when we come to it. I wanted to kind of plant those seeds, though, right now of this idea of a restricted domain and kind of bring that back up, because it was something that we talked about briefly last year in our Algebra 3-4 class. And this is also worth pointing out. This is the reason why I swapped the x's and y's last. Because if you swap the x's and y's first, what do you do with this x is greater than or equal to 0? It doesn't really make sense how it's getting rid of the plus or minus. By doing the swapping of x and y's last, it's very clear how to use that restricted domain to ensure that we have a function there. So that's why I choose to do it in that order, is to do the swapping of x and y's last, is if I run into one of these restricted domain problems. There's no question for me about how to use that information. Let's do another. So here we have f of x equals the square root of 12x plus 5. I'm going to start the same way. I'm going to rewrite using the y equals notation. And then I'm going to try to get the x by itself. What would be the first thing I'd want to do to get the x by itself here? Square both sides. That's good. Then what should I do? Subtract 5. Very good. And lastly, divide by 12. Now that the x is by itself, I can swap my x's and y's. And say that f inverse of x equals x squared minus 5 over 12. Everybody okay with that idea? Do you see anything fishy about this inverse? It's a little bit harder to notice what's going on or why there's a problem here, but there is kind of a big problem. Let me illustrate to you what's the issue. Let's say I do f inverse of negative 2. If I do that, I get negative 1/12. Everybody agree with that? So what that tells me then is the point negative 2 comma negative 1/12 is in the set f inverse, right? That's a point on f inverse. So that would tell me then that negative 1/12 comma negative 2 is a point in f. Everybody agree with that? So, but what that would imply is that somehow I can take the square root of 12x plus 5 and get a negative number. Not quite right there. Does everybody see that? So we do have a little bit of an issue going on here. I'm not going to worry right now about like how to fix it or what the issue really is. Again, this can be solved by doing a domain restriction, or in this case, like a domain extension. But we'll talk about, when we talk about inverse trig functions, this becomes an issue later on that I just want to illustrate to you. Like, sometimes our inverse is too good. Like, does it contain the transpositions of all the points in f? Yes. Does it contain other points that are not transpositions in f? Yeah. So it's too big. Our inverse has too much stuff in it. We would need to chop it down a little bit to make it actually work. And we'll talk later about how we actually do that chopping. But that's kind of what's going on here. So that's much harder to see than the other one with the plus or minus being not a function. Here where our inverse contains too much. Okay. Let's do another example here. So g of x equals 1/2 times 3 to the 4x. And just like before, we'll rewrite using y equals notation. And then we'll solve for x. What's the first thing I'd want to do here to solve for x? Multiply both sides by 2. That's the same thing as dividing by 1/2, if that's what you were thinking. Obviously, multiplying by 2 is a little bit neater of a way of saying that. Nobody likes dividing by fractions. Okay? What's next? So we have 3 to the 4x, right? Yeah, so I have to use a logarithm. Very good. Which logarithm should I use? Log base 3. Now, any logarithm still works, but it's much messier. Log base 3 is the neatest way to do that, and that's the one that we will use here. I want to be clear, though, you didn't have to use that one. It just makes your life a little bit easier to use log base 3, and I'm all about making my life easier. My life is hard enough. Facts. All right. And then my last step then would be to, well, let's divide by 4, right? So still need to do that. And I'm going to write it as times 1/4. When there's a logarithm involved, kind of the convention is not to write the logarithm as a numerator of a fraction. But if it's just a coefficient like that, we would just, bless you, stick it in front. Would I mark it wrong if you wrote it as a fraction over 4? Definitely not. But if you're taking a multiple choice test or something, I would suspect that that would not be the way they would format the answer. That they would have it written as like 1/4 times the logarithm, yada, yada, yada. So I just wanted to be clear. Somebody asked, I wrote it that way in a previous class. And that's really the only reason. And there's no issues with these logarithms, or I'm sorry, with these functions and inverse. These work as expected, so there's no issue there. Mostly because the domains and ranges are appropriate, like they match up appropriately when we do the swapping. So the one function doesn't contain anything the other shouldn't. Are we on D is the next letter, I think, right? Alphabet's hard, guys. So here we have h of x equals 5/3 times the natural log of 7x minus 1. Just as an FYI, those of you that haven't had me in class before, when I write my logarithms, I always write them cursive, like in script. The reason I do that is so that when I'm looking at my paper, I can't accidentally confuse log as 10g, or I can't confuse ln as 1n, because those L's and O's look a lot like 1s and 0s. It's easy to sometimes get turned around, especially when you're looking back at notes where you haven't been using a lot of logarithms. When you encounter it, it's easy to kind of mistake what that is. Whenever I write mine, I write them in script. So when you see the messy cursive, it's probably a logarithm. I acknowledge my penmanship is less than spectacular, but if you ever have questions about any of that, let me know. It's important that you can read what I wrote down. Okay. So we'll start by doing the same thing. We'll rewrite using the y equals notation. And then my first step should be to multiply by 3/5. Sounds good to me. That's the same thing as dividing by 5/3, but nobody likes dividing with fractions. Just multiply by the reciprocal, right? So this natural log here, does anybody remember what a natural log is? The same as? Yeah, well, it's log base e. Yeah, that's correct. Good job. So to cancel out that natural log, what do I need to do to both sides? We use the exponent base e. So when I write these, I always write that exponent base really big. So I can't confuse myself and think that I'm multiplying both sides by e. my old equation becomes the exponent, and e is the base of that exponential on both sides. The e cancels out the natural log, and we're left with just the 7x minus 1. Sometimes I'll just say that as big E to both sides because I write it gigantic. It's comical, but it does the trick. And to finish this out, we'll add 1 and divide by 7. So I have this. Yes. H of x is the function? Yes. That's okay. You can make sure. Plus 1? No problem. And again, on this, there's no issues with these inverses. Again, the domains and ranges for logarithmic and exponential functions match up the right way, so we don't have to worry anything about that. That finishes up section 7. Let's move on to section 8. That is C. Yes, Ben?
Number 4 is that if the absolute value is C, that would be A.
Oh, those are supposed to be A's. Thanks, Ben. Wouldn't make a lot of sense if they were C's. Good catch. So, what we said here is that every member of a family of functions can be written as some transformation of the parent function, where that general form of any member is y equals a times f of 1 over c times x minus h plus k, where the c's control the reflections across the y-axis and the horizontal stretches and shrinks. The a controls the reflection across the x-axis and the vertical stretches and shrinks. The h's control the left and right translation, and the k's control the up and down translation. And hopefully this looks reasonably familiar from Algebra 3-4 last year. We didn't include the 1 over c's for the most part because the things that we looked at last year, most of them, every time you had a horizontal translation, you could write that instead as a vertical translation. For example, if you have an absolute value graph that looks like a V, if I horizontally stretch that, that's the same thing as like vertically compressing it. So if we have a certain kind of symmetry, those two kind of transformations are the same. And most of last year we didn't acknowledge the horizontal transformations because you could do it with a vertical transformation. That won't be the case for most of these trigonometric functions, so we do need to be a little bit more careful about that, and that's why I've included the 1 over c's here that we didn't do a lot of last year in Algebra 3-4. Is everybody okay with that idea? Okay. Okay. Yes, Ben?
All the letters at the bottom are intentionally double.
One of them has an absolute value intentionally and the other does not intentionally.
The left and down one?
Correct. And the reason is because the sign on the H and the K dictates the left or rightness. So I wouldn't say left -3 units, I would just say left 3 units, right? Even if the H was -3, the negative tells me left, and then the size of the H tells me how far left.
It says if H is less than 0, are those absolute values?
No, because obviously if you take the absolute value of H, it can't be less than 0, right? So those are correct as they should be. Good questions. I suppose here you don't even really need the absolute values if you don't want them. Because if it's non-zero, it'll be non-zero even if it's an absolute value or not. So, all right. Let's look at some examples of the kinds of things I'd expect you to be able to do with this information. Stop talking, please. Thank you. So let's say we ask you to describe the transformation of f of x. And I tell you that we have 2 times f of x plus 1 plus 4. The first thing I'm going to do is identify my values for a, c, h, and k. What's the value for a here? 2. What's the value for C? One is correct. The value for H is? The value for H is -1. And the value for K is 4. So I'm going to use these values and that sixth set of criteria above to describe this transformation. So the way that I'd like you to do that is we're just going to number this 1, 2, 3, 4, 5, 6, just like the sixth set of criteria that we listed above. And if like criteria 1 is satisfied, we'll say like what it does. For criteria 1, we have to look at the sign of the C value. Since C is positive, nothing happens for step 1. I'll just put a slash there to indicate that like nothing happened. Everybody okay with that? Step 2, we have to look at the magnitude of the C value. Since the absolute value of C is 1, nothing happens in step 2. Step 3, we have to look at the sign of the A value. Since A is positive, nothing's going to happen in step 3. In step 4, we have to look at the magnitude of the A. Since the absolute value of A is greater than 1, we have a vertical stretch by a factor of 2. And yes, I do need you to write by a factor of 2. For 5, we have to look at the H. Since the H is non-zero, it does something. Since it's negative, we go left. And since the magnitude is 1, it's 1 unit to the left. 6, we look at the K. Since the K is non-zero, it does something. Since it's positive, we're going to go up. And since the magnitude is 4, it'll be 4 units. Everybody okay with that there, Caden? Yes. Even if you're not doing all of them, I'd still like you to write it out and just put a dash next to it or whatever. Ben? Yes. You will want to have those memorized. We're going to use them a lot. So let's do one more example of this. So here we have -3 times f of 2x minus 4 minus 2. So again, I'm going to start the same way. I'm going to write my values for A, C, H, and K. My value for A is -3. My value for C is what was that? The value for C isn't 2. So remember what this looks like. So the coefficient on our x is 2. So that's 2 is 1 over c. So if I take the reciprocal, I'll get my value for just c. C is 1/2. So in general, c is going to be the reciprocal of that coefficient on x. Is everybody okay with that idea? What's my value for h? Not 4. Not -4. It is 2. Why is it 2? Notice here, this is in a factored form, is it not? So my h is really sitting there. Everybody's okay with that? That was a little tricky, but once you've seen that trick, you'll know, oh, okay, I got to make sure I factor that inside part if I can. And then the k is -2. So I'll write out my 6 steps here. Do they have to be in the same order? Yes, the order is important. I need you to write them in 1, 2, 3, 4, 5, 6 order that I wrote them for you guys. I'll explain why in a moment. Step 1, we look at the sign of C. Since C is positive, we don't have to do anything for step 1. For step 2, we look at the magnitude of C. Since the magnitude of C is less than 1, we have a horizontal shrink by a factor of 1/2. In step 3, we look at the sign of A. Since A is negative, we reflect across the x-axis. In step 4, we look at the magnitude of A. Since the magnitude of A is greater than 1, we have a vertical stretch by a factor of 3. In step 5, we look at the h. Since the h is non-zero, it does something. Since the h is positive, we're going right. And since the magnitude of h is 2, we're going 2 units to the right. And in step 6, we look at the k. Since the k is negative, we're going left. And since the magnitude of k is not left, down. And since the magnitude of k is 2, it's 2 units down. Now, I said the order in which you write these is important to me. I need them written where in the same order that we recorded them earlier. The reason that is because this is the order that if you're going to apply these transformations to a function one at a time, this is the order you would need to do them in order to get the correct resultant function. So not all these transformations are commutative. So if I go left 2 and up 2, that's the same as going up 2 and left 2. However, if I, like stretch something vertically and go left 2, that's not going to give me the same result as going left 2 and stretching something vertically. There, the order matters. So we need to make sure we're doing the transformations in the correct order to get the desired result. And the way we're going to make sure we do that is by recording these steps in the correct order. So I need to make sure they're written 1, 2, 3, 4, 5, 6 are the same 1, 2, 3, 4, 5, 6 that we've recorded. Or we do the stuff with the C's first, and then the stuff with the A's, and then the H's, and then the K's. Okay with that idea? Suppose that we have the graph here. Let's say this is our parent function, y equals f of x. And let's say that we want to graph the transformation g of x equals 2 times f of x plus 3 minus 1. So one way I could do this is to apply the transformations in the order that we would report them. So I would start by listing them just like we did before. So in step 1, we're dealing with the C's. My C is 1 in this case, so nothing happens for steps 1 and 2. For step 3 and 4, we worry about the A. Since the A is positive, nothing happens in step 3. But since the magnitude of A is bigger than 1, in step 4 we have a vertical stretch. In step 5, we worry about the H's. Since the H is -3, we're going to go left 3. And in step 6, we worry about the K's. Since the K is -1, we're going down 1. So if I were to want to graph this, what I'm going to do is I'm going to do 4 steps. Oops. So I'm going to first graph the vertical stretch in purple, and then I'm going to take the purple graph and do the transformation left 3 units and write that graph in blue. And then I'll take that graph, the blue graph, and do the transformation of down 1 and draw that graph in orange, and that orange graph would be the final graph. Everybody okay with that plan? Okay, so if I was going to do a vertical stretch to this, how do I go about doing that vertical stretch by a factor of 2? What do I have to do to the coordinates in my graph in order to do that? Jackson, what did you say? Multiply them by 2. That's almost correct. When you say them, what do you mean? Just the y's. Why the y's? Y's do up and down. That's vertical direction. So we're going to just multiply the y coordinates by 2. Hi, Annika. Thanks. So when I multiply -2, 0, the y coordinates by 2, I just get -2, 0. Nothing changed. The next one I get 0, -4. The next one, nothing changed. And then this last one I get 4, 8. Everybody okay there? If I want to go left 3 units, how do the coordinates change? Subtract 3 from the x-coordinates. Good. So -2, 0 becomes -5, 0. 0, -4 becomes -3, -4. 2, 0 becomes -1, 0. And 4, 8 becomes 1, 8. Everybody okay with that? And if I want to do down 1, what do I do? Subtract 1 from the y's. So this becomes -5, -1. And then I have -3, -5. And then I have -1, -1. And then I have 1, 7. And then I have a big mess. Is everybody okay with what we did there? Now that was a little bit time consuming and pretty writing intensive and got kind of messy by the end of it, right? Is there an easier way to do this? Yeah. Of course there is, right? So I can just apply my transformations all at once using this formula. Is this something you'd probably want to have memorized? Yeah, that would be a good idea. So in their case, C was 1. The first point's x value is -2, and our h value is -3. Our a value was +2. The y in that case was 0, and our h value is -1. So that gives me the 5, -1, which is what that point -2, 0 turned into. If I take 0, -2, so 1 times 0 plus -3, 2 times -2 plus -1. When I do that, I get -3, -5, which is what that second point transformed into. Yada, yada, yada. So this idea that we did here at the end is a very, very important one. This is actually how we're going to do the majority of our graphing of these trigonometric functions, is we're going to identify some key points on the parent function, use our values for a, c, h, and k, and use those to transform the key points of the parent function into the desired coordinates, and then graph our new points. Okay with that idea? Okay.